All right, so just a couple examples here to get us started thinking about what it means to have systems of linear equations with three variables, right? Because the reality of our life is that a lot of the things that we are involved with are fairly complicated. There's not usually just like two different things that relate to each other. There could be three different things, and then having to think about how they relate and puzzle out like how much each thing is worth or how many of something there are might be kind of challenging if we don't necessarily have kind of nice numbers and nice relations, right? And so what we're going to take a look at in this next section is really an extension of what we learned with our 9.1, thinking about our two variable one. Okay. And so the reason why I was highlighting so much in 9.1, like the strategy, like how do we do this? How do we do that? Is because for 9.2, when we're looking at three variables and we're trying to solve a system, we end up with situations where we need to really drive that problem solving technique. We need to think about what makes sense for us, and a strategy that works for us might not work for someone else, or that might not be how they see it. So there's a lot of different ways to approach these problems. And really what I want us to get out of this is learning like what are strategies that we go to solve these problems? What are strategies that other people go to solve these problems? And how can we sort of be very intentionally strategic to solve these problems, okay? And so what we're going to do is actually skip the next page for right now. We're going to go right into an example to kind of see like how it's done and use this as a chance to talk strategy. All right. So I would encourage you folks to throw your ideas into the chat if you are not feeling comfortable yet with, putting your idea into the whole chat. You can always send me a direct message. That is fine as well. You can speak out loud, whatever serves you. But I would really love for this problem solving to be a collaborative experience for us. I think that it would be important to think about what ideas we have and what ideas other people have so that we can add some tools to our toolkit. Okay. So let's take a look at this example number one. All right, so this is what I mean when I say now we have a system, right? So a system of equations, but this time we have three systems in our, or three equations in our system, and we have three different variables. And our goal at the end is to find a value for X, a value for Y, and a value for Z, okay? So let's do this. All right, I'm going to give everyone some think time first, because I think that it's important to acknowledge that sometimes we just need to sit with it for a little bit, let it marinate before we start throwing out ideas, right? So we're going to take about 3 minutes, all right? You might get it all done in that time, you might not, but the goal here is to write something down, okay? So take 3 minutes, write some stuff down, see what you can find, and then we'll come back together as a whole class, okay? All right. And again, I think we work through these problems at different speeds, and some of us are really adept at finding those strategies, looking past the letters and thinking more about the strategy. And some of us are still really learning that technique. But it is a skill that I hope we develop over the year. I think that this idea of problem solving rather than just like doing 20 of the same kind of problem is a really important part to develop in our mathematical selves. So, what strategies do we think?
I tried cleaning for a single variable,
Mm-hmm.
but I think that method is kind of long.
So you tried to get all three equations as a single variable?
I only tried with the first one so far. So I did x equals 9 plus 2y minus 3z, for example.
So solve for one variable. Okay. What are some other thoughts?
What I did was put the first equation and then added the second equation to get just a like the y and z by themselves. And then I did the first equation plus the third equation to get another equation by itself.
So far I'm hearing that maybe we solve for one variable. Maybe ultimately this leads to substitution, possibly. I see another idea, maybe use elimination so we can get rid of one variable.
In my case, I had the first two equations both equal x, and then I had whatever was left over would equal each other, which then would cancel out and get you y and z as the variables, and then you can substitute y into one of the x equations to get only z. And then from there, if you use the second equation and have it equal z, you can get the full answer for what z would equal. And then from there, you would substitute the number back into the equations to get x and y.
Yeah, we could certainly solve for one variable and then use that to get the other two values for sure. Now, I think that we all come in here with different strengths, right? Some of us are really good at seeing big picture. Some of us are really good at computing. Some of us are really good at proofreading other work and being like, oh yeah, that's definitely not right. But regardless of what strengths that we bring to this, it's important to kind of think about like, seeing it from someone else's perspective, right? And so let's kind of set one up together. And the strategy that we're showing here is neither right nor wrong, nor the only way to do it, right? We've only taken a poll of 3 people, and each of these 3 people had a different approach, right? And I see one more even there in the chat. Good, okay. And so that's actually where we're going to start. So Jesus, thank you so much for pointing that out. That was my first instinct as well, that if I could at least get rid of one letter, maybe I could start to see where I could go with that, right? And so again, just because this is my method, it doesn't mean that that is the only way to do it or the best way to do it, okay? So let's kind of take a look at that, all right? We're going to take a look at these 2 equations, and we'll call this step 1. And we're going to add equations to eliminate. All right. And I think when I add the equations, I get y plus 2z equals 3. Is that true? Is that what other folks got? Y plus 2z equals 3. Okay. Cool. All right. So the reason why I wanted to do that, add equations to eliminate x, is since x and negative x have the same coefficient, but opposite sides, right? So that is one of the clues that we had mentioned from when we should use elimination. Now, that's all we got, and there's still all these other equations to do, but I wonder if I could find another equation that also had y and z, then I've made it just like the questions I saw in 9.1. And so I'm wondering, of these three equations right here, which ones could we pair together, get rid of the x, and only have an equation with y and z?
You could multiply equation 1 by 2 and then, or -2, and then add those, the 1 and 3 together, like the first equation and the third one.
Perfect, perfect, right? If I could make this be a 2x, then it would match with that one, then they would go away, right? And I love even that you were like, ooh, -2x, because then I could add. Now look at what we have in this second equation though. We already have a -x. I could also take this equation, multiply it by 2, and then already have that negative in there. It's really up to you in terms of what you choose to do, but maybe let's do this. Step 2, multiply second equation by 2 and combine with equation 3 to get rid of x, right? So if I multiply that second equation by 2, I get -2x plus 6y minus 2z equals -6. And if I stack that on top of the third equation, I get 2x minus 5y plus 5z equals 17. And now I can add those together and I get y plus 3z equals 11. True, false?
False, because you got to multiply the -6 by 2.
Right? Whatever we do, we better multiply that whole equation by 2. That means this -6 actually should be a -12, which would change. Let's see, -12 plus 17 will give me +5. Okay. So easy to make that mistake. And so that's why we need to be super careful about making sure that we've distributed everything we need to distribute. Okay. All right. Well, check out what we have here now, folks. We have one equation with y and z. We have a second equation with y and z. And so what we can do in sort of this third step is combine the two equations that only have y and z. All right. So how do we combine these? We want to use elimination. Do we want to use substitution? What would be helpful here? We could use elimination for sure. And maybe one thing that tells us that we should use elimination is the y has a coefficient of 1. And so does the x, or so does the other one, right? Both y's have a coefficient of 1. Now, it doesn't matter which one you sort of stack on the top and which one you stack on the bottom. If I put this one on the top and I put this one on the bottom, I want to make sure that let's do this in blue, subtract the entire equation, right? We can choose which one we put on the top or which one we put on the bottom, but at the end of the day, we need to make sure we're subtracting the whole thing. Oops, that's a plus. All right, so we subtract, we get y minus y is 0, 3z minus 2z is 1z, 5 minus 3 gives us 2. So we found z, right? And I know that was a lot of work and a lot of thinking, but we found z. What is a reasonable thing to find next?
Why?
What makes you say why?
Because we have a formula. We have two formulas actually that have only y and z. So if we have our z, then we can find y.
Perfect, right? I have z. So now let's go backwards from where we got this from. We could go in here, and we could find what y is, or we could go over here and find what y is, right? So choose your favorite one. Go ahead and plug in our value for z, and let's see what we get for y. And I'm going to use the y plus 2z one, just because the numbers are smaller, but you can certainly use the other one, that's fine too. And I think we get y equals -1. Right. So a lot of thinking that's happening so far, strategies to make it into the kind of problem that we know how to do, actually doing the problem, but we still have one last step, right? And that last step is we want to find x, because in order to solve all of this, we need an x and a y and a z, okay? So how do we find x? What are our options to find x?
Since we have like z and y, and we have like a positive x equation up there, we could probably just plug the two variables that we have into that.
Yeah, I agree. We can go back to any one of these three, but which one will be the most efficient? Probably the first one, because you're right, x is already positive. If I plug it into the second one, I'm going to get a negative x, which is fine. I can divide by -1. Or if I plug it into the second one, I'll have to divide by 2 to get x. And those are all things we can do. But at the end of this super long problem, maybe we choose the one that takes up the least amount of brain space, right? I don't have to worry about dividing anything at the end. But I can say that x minus 2y plus 3z equals 9. And I can plug in my values for z and for y. So y plus 2 plus 6 equals 9. And if I solve for x, I'll get x equals 1. Okay. So we found values for x, y, and z. But I want us to write out in words what this means, okay? So this system has a single solution. All three planes intersect at the point 1, -1, 2. All right, so the system has a single equation or single solution. All three planes intersect at the point 1, -1, 2. All right. And so if we kind of go back up to this chart that I was like, let's not fill that in yet. All right, we've got a bunch of pictures. But what's happening, and this is why we don't usually solve these graphically, is we're drawing planes, right? Or like sheets of paper. And where do those sheets of paper intersect? And so we want to actually note right here that we're looking for intersection of planes, not right? So planes like a sheet of paper, not that thing that flies in the sky, okay? And this first picture actually tells us about what a single solution looks like, right? So the single solution is right in there. Three planes intersect at one point. Right? So three planes intersect at a single point, and algebraically, what you're going to end up with is x equals a number, y equals a number, and z equals a number, just like we did in example 1, and our solution would be x, y, z. Okay. So when you solve the question, you're able to get a number for x, y, and z. What that means is you have a single solution, three planes intersecting at a single point. Okay. All right, so let's take a look at example number 2, okay? And I really like how thoughtful people were in terms of contributing their ideas for number 1. And so I'm going to suggest that we do the same thing again here. Let's take 3 minutes on our own and just kind of start playing around, right? What can we do? It doesn't matter how far you can get. It matters that you're brave enough to put something down. Okay, so let's try and see what we can do for this. We'll talk through some strategies and then we'll kind of pick one and maybe go with it, or maybe we'll blend a few different strategies together. Okay. All right. I know that was only 3 minutes, and sometimes that doesn't feel like enough time, but what are some initial thoughts in terms of strategy? What can we do here?
Well, I thought that since x, like the first two equations, we already have a positive and a negative value, we can just do the process of elimination for those.
Yeah, I love it, right? We just saw this structure and it showed up in a different problem. And so if you're able to identify that same structure, that's awesome, right? Because the numbers are different. But the idea that we can get rid of x here is the same, right? So eliminate, let's put a 1, eliminate x. And so if we eliminate x, I think, double check my arithmetic here, we get negative y minus 4z equals 7. Is that true?
Yeah.
Yeah, okay. All right. So if we wanted to do that and continue in that same vein of thinking that we did from the previous problem, what would be a reasonable next step? Perfect. I love it. We're going to take that second equation, we're going to distribute a 5, and then we can get rid of the x's in that one as well. Love it. So step 2, eliminate x by multiplying second equation by 5. All right, so let me actually multiply by 5, negative 5x plus 10y minus 25z equals 15. Yep, I think I multiplied everything by 5, right? I didn't forget to multiply that right-hand side like I did last time. And I can stack that on top of that third equation. Add them together, we get negative 3y minus 12z equals 23. Okay, cool. So we've got two equations now that only have y and z. Great. What do we do with those?
What I did was I took the top one, multiplied everything by 3, and then subtracted those two equations. Or I guess once you're done distributing, then subtract it by the negative 3y minus 12z equals 23.
Yeah. Right, we're going to multiply by 3. Alternatively, we could multiply by negative 3, right? Your choice. And so if we multiply by 3, we get negative 3y minus 12z equals, let's see, 3 times 7 is 21. I'm going to stack that on top of the other equation. And I'm going to be really careful to subtract here, right? Because the goal of subtraction is to get rid of one of the letters. All right, so negative 3y plus 3y gives you 0. Negative 12z plus 12z also gives me 0. So on the left-hand side, I have 0. What do I get on the right-hand side? Yeah, we get a 21 times or minus 23 gives me negative 2. Okay. So we get to this point in the problem, and some of us might start to panic a little bit, be like, oh no, I don't know what that means. Like in the previous problem, it gave us a value that we wanted, right? It gave us a value for y, or it gave us a value for z, and then we could finish the whole problem. But now we have a statement that says 0 equals -2. Okay. This is where you need to put aside those insecurities you might have about doing this kind of complicated math, right? And return to some basics for a moment. This statement right here, 0 equals -2, true or false? I've been asking you guys that a lot today, but is 0 equals -2 a true or false statement? Yeah, that's 100% false, right? Okay. So here's what this means. If you work through a question, you're doing all your things, you checked all your signs, and you get to the end and you get a false statement. Here's what this means. Okay. There is no solution for this system of equations. Right? There's no solution for this system of equations. That is, there is no point or line where the planes intersect. Okay. It's okay to get a false statement. All right. This is why this is only our second example, but already we're getting a false, right? Sometimes I feel like we do so many like example 1 that we never get to this, and that's why it's uncomfortable. But I want us to just be aware that it's okay to get something that is false. And now we just need to know what that means. Okay. So let's use this, go back up to the pictures and see which one this falls, which category this falls under. Okay. So if we return to this table with these lovely diagrams, we found a system that looks something like this. Okay. And there's 3 different pictures here because it could be any of those 3. We could have this where it's like sheets of paper in your notebook, right? They don't intersect each other. Like something went really wrong if one of the pieces of paper in your notebook goes through another page, right? Might mean you were like erasing too vigorously, whatever it is, things got crumpled, the paper got wet, but there might be a hole in your paper, right? But when we have just sheets of paper or planes that are parallel to each other, they never interact. And so it's okay that you get an answer like 0 equals -2. All right. But if we think about other ways that we can have planes cross, but maybe all of them don't cross at the same place, we could have like 2 planes cross here, 2 planes cross here, 2 planes cross here, but they're never all in the same place at the same time. Right? And picture B is like a different variation on that. The green and the blue cross here, or sorry, the green and the orange cross here, and then the blue and orange cross down here, but they don't all 3 ever meet at the same time. And maybe you could think about this as like, if you're trying to schedule some hangout time with your friends and you're like, okay, everybody, can we meet at this time? And they're like, no. And someone's like, oh, but I could do this time. Someone else is like, I could do that time. Someone else is like, I could do that time. Like, it's not necessarily helpful because if you want everyone in the same place at the same time, it's not really possible given these constraints, right? And so we call this one no solution. Okay. And what it looks like for you is you might get a statement like false statements such as maybe you get 0 equals 3, right? That's definitely not true. Or 5 equals 1/2. That's definitely not true. Or maybe you even get -4 equals a +4, and that's definitely not true, right? So if you get any false statement, in your head, you're like, oh, that's like trying to organize plans with a group of people whose schedules don't really work together. It's okay if we can't find something that works for everyone. Okay. All right, let's do one last example here. I know we've had a lot of letters, a lot of problem solving today, but let's do one last example here. All right. So same thing. Let's take just like 1 or 2 moments, take a look at this question, and let's start sharing strategies for how we might want to approach this. Okay. So take a moment and look at it. We're not going to have the full 3 minutes to think through, but any ideas that pop into your head that you might want to try, just go ahead and toss them into the chat or share them out loud.
The first equation and third equation have a y that's like either plus or negative, and so we can add those two to eliminate the y.
Great. All right. Very clever, right? So far, we've been looking at just the x's being the same, but it's worth our time to kind of scan through the equation and see if anything else is the same. And it turns out that we have a y and a negative y. So even though in the past we've gotten rid of all the x's first, maybe in this one, we eliminate y first, and that's okay too, all right? So if we eliminate y, we're going to get, let's see, 2x plus x is 3x minus 2z equals 0. Okay. If we choose to do that first, what would be a good next step to make?
Then we could multiply the first equation by -2, and then add the first and second equations so that we can eliminate another y, but just with a different equation.
Perfect. Eliminate y by multiplying the first equation by -2, right? But the thing I don't want you to miss about what was just shared is that if we eliminate y here, our goal should be to eliminate y from a different set of equations, right? If we eliminate y in one of them, but like z in the other, we're not creating a system of equations that only have the same 2 letters. Okay, so it's on purpose that we're trying to get rid of the same letter in 2 different sets of equations. And so if we do that, we'll end up with, let's see, -4x minus 2y plus 6z equals 0. And we'll stack it on top of the 4x plus 2y minus 6z equals 0. All right. What do we get when we add those together? Okay. 0 equals 0, right? And maybe like above, this is where you sort of hit a panic moment. You're like, oh my goodness, I did something definitely wrong because everything went away. I don't even know what to do with my life anymore, right? Like it tends to be really scary when we get answers that don't seem like they should be okay. All right. But let me ask you the same question I asked you about this one, right? When I said, is 0 equal to -2, true or false? We all said false. And you were all correct. Is 0 equal to 0?
Yeah.
Yeah, that's a true statement, right? So let's go ahead and note here, this is true. Okay. So if this is true, it's not going to be a no solution situation. Okay. Rather, here's what this tells us. So if you get to the end, you get a true statement. It means that this system of equations has infinite solutions along the line all three planes intersect at. Okay. The system has infinite solutions along the line that all three planes intersect at. All right. So let's go back up to that chart. All right. We'll fill in that last little slot for the chart. And that is this second picture. Okay. So in this case, we can see that the orange, the green, and the blue plane all go through the same line. All right. So we call this our infinite number of solutions along the shared line. All right. And we want to say that it's different from the first one because it's not three planes intersecting at a single point, but three planes intersect at a single line. Okay. And so in contrast to the no solutions, we don't want false statements, but we want true statements such as 0 equals 0 or -2 equals -2. All of those are okay. All right. So 3 different cases, just like we have with the system of 2 equations. But I've got a great question in the chat that I want to address here. And so this question is, could we have known from the beginning because they were all equal to 0? Okay. And the answer is sometimes we know and sometimes we don't know. All right. So it would be important to sort of go through a little bit of this to make sure that you end up with a true statement. Because the tricky thing here is 0 has some really nice properties that maybe if they were all equal to like 2, we might not get those same properties. Okay. So really great questions here. Really great thinking through problems. I love how people are picking up on different techniques that other people are using and thinking about how to apply those in a different context, right? And so what we'll find here below is, in case you want to go back and do a little bit more practice, you've got an example 4 here, got an example 5, and you've got an example 6. All right, so you can feel free to take a look at these on your own time and think about which of the cases we have above. And I will tell you that examples 4, 5, and 6, of the 3 questions, one of them is going to be where they intersect at a point. One will be where they intersect at a line, and one will be where they don't intersect at the same point or line ever. Okay, so you don't know which one's which, but there are one of each of those in these extra 3 practice problems. Okay. And so with that, let's go ahead and stop that recording.